Thank you very much. So yes, my name is Kevin Backhouse. I'm a member of SEML's security research team. And I'm going to be talking about some vulnerabilities I found during the course of 2018 in iOS and macOS. So what I'm really talking about here is the XNU kernel. It's shared between both iOS and macOS. So if you find a bug in XNU, then that typically means that you found something in both of those platforms. Okay, so this is really a story of 3 bugs. As you can see, there's more than 3 CVEs, but I think of these as really just 3 bugs because what happened here was that there was kind of multiple variants of the bugs. To a certain extent, it's also the story of my career so far as a security researcher. I'm approximately the right age that I could have been in the Cult of the Dead Cow with Beto, but in fact, I didn't do any of that stuff when I was a teenager. I didn't do anything related to trying to hack or break anything prior to 2017. So this bug here was one of the first CVs I ever got, and as you'll find out in a second, I really didn't know what I was looking for when I found that. And at the time, it actually felt kind of like a fluke. I thought, I'm never going to find anything like this again. But in fact, so I mean, what you'll also see is that this packet mangler bug isn't nearly as exciting in terms of like the severity of the vulnerability as the ones that came next. But what it did do was it taught me about what might be interesting to look for, and that's what led to me finding these other bugs in XNU. Okay. So there's also going to be a few extra topics during the course of the presentation. Some of these things are potentially a bit dull. So what I'm going to do is I'm going to try and weave them in when it's actually relevant to the story. So I'm going to focus on the bugs, and I'm going to talk about these things when it's relevant. Okay. So we'll just start with the packet mangler bug. This is a cartoon that my son drew. I kind of explained to him roughly what happens, and he likes drawing cartoons, so he turned it into a little cartoon for me, which I think is pretty cool. I've got one of these for each of the 3 bugs. So just to explain quickly who the characters are, this he's called Eve999, and he's a cyborg. He's one of the heroes, and this is one of the other heroes called Atom Man, who's a huge living atom. So what happens here is they receive an evil packet, and they say, what should we do? And Atom Man says, let's mangle it. And as you can see, that doesn't work out so well for them. This is the villain. This is Slow Sally, who is a robotic car. So let me just show you now a quick video of what this looks like. So I can send something over the network that is going to crash the Mac. Now, the reason that this is not as exciting as some of the bugs that I'm going to show you later is because it only works when the packet mangler is switched on. And so the packet mangler, it's in the kernel, but it seems to be some sort of vestigial thing that doesn't actually get used. So although it's there and you can switch it on, you need to have admin privileges to switch it on, and nobody, as far as I can tell, ever does that. So I got a CVE for this, well, multiple, but the severity isn't all that bad because of the fact that the packet mangler is not switched on. But I do think the code is really interesting to look at, and so that's why I'm going to be talking about this first. Next slide. Okay. There we go. All right. So this was one of the first bugs that I ever found. So I didn't really know how to find security vulnerabilities. And so I was kind of sort of just hunting around in the dark. And so I was just looking for generic stuff. So what I decided to look for was, can I find anywhere where there's an array index that might have an integer overflow in it? That could potentially be a security vulnerability. So what I'm going to show you now is QL, the query language that I use to find this stuff. This is free. You can, I mean, it is a product that's made by my company, but this is all free. So everything I'm going to show you here, you can download and you can try it yourself on any open source software. So what I've got over here, just in the left-hand column, so you can see I've got snapshots for the all of the recent versions of the XNU kernel that Apple have published. I think they're beyond 10.14.1 at this point, but they haven't published the source code yet, so that's all I've got. But this was something I found in version 10.13, so I can click on that and I can say use this database. And so then the array, the query that I wrote was very simple. It just said, find me basically something like this. You've got an array indexing expression, and it's got an add in the index, and there's a possibility that the index might overflow. And so you run this query, and it found a few things. A lot of these turned out not to be interesting, but this one was. So this is in the packet mangler, and it's adding these two variables I and j. They're both ints, and our range analysis is not able to prove that this can't overflow. Now, a lot of the time when you do range analysis, it's very difficult to actually come up with accurate results. So a lot of the time when you're looking for overflows in C code, you find that almost anything might overflow because range analysis isn't smart enough to be able to understand the kind of subtle invariants that are going on. But in this case, it turns out that it was totally right because they're doing stuff like this. They're just doing plus equals on the I. And if you go and look at the loop that it's in, TCP opt-len is one of the things that it's looping over. It's just going to stop when the thing is 0. So it's really not written very carefully. TCP opt-len, they're doing stuff like this. So as an attacker, you can easily make that overshoot go negative, and then the loop is just never going to end. So the other thing that's happening here is that this array here is on the stack. So this is, in fact, a potential stack buffer overflow, where you're writing potentially beyond the end of the array. Now, just to quickly show you, so MP TCP opt-len, that comes from here, TCP opt-buff. So let me go back to the presentation now. So this is a tweet that I kind of agree with. I feel this way as well. There's a lot of stuff that I've kind of started to learn about as a result of being a security engineer that I never would have bothered learning about otherwise. So this is the first one. So TCP/IP packet structure. I guess a lot of you probably already know about this already, but initially you have 20 bytes of the IP header, and then you've got some IP options, often 0, but you can put options in there. Then you've got the TCP header, which is also 20 bytes, followed by the TCP options, and then the payload. The payload, I think in theory can go up to 64K, but in practice is almost always less than 1,400 bytes. Now, of course, normally when you're using TCP sockets, you don't need to care about this stuff at all because you just open a socket, and the whole point of TCP is that it breaks it up into packets for you. You don't need to worry about that. You just send a stream of data and it gets received on the other end. But if you want to try to write a POC for a vulnerability, then you do need to use this stuff sometimes. So from what I've seen, we'll come back to this later, the IP options almost never used. They're almost always 0, whereas the TCP options are actually quite frequently used. TCP packets often have options in them. And so that's the data that this code is reading. This is that section of the header where the TCP options are. So this is attacker controllable. I mean, you can send a network message over Wi-Fi with whatever you like in there, and it's going to read it directly out of there into MP TCP oplen. And in fact, the way that they've declared this, they've declared it as char, so it's a signed number. So you can actually make this thing signed if you feel like it. Okay, so next step. Now we need to learn how to do raw socket programming. Again, this was something I didn't know about before. This first one is the link where I found sample code to learn how to do this. Having now done it myself, you can also see it on our GitHub page. The POC that I wrote for this is on our GitHub. Raw socket programming basically means filling in the headers yourself, and these are the kind of basic steps. So what you do is you open the socket with sock raw, and then you tell the kernel that you're going to include your own headers. It doesn't need to add the headers for you. Then you obviously need to initialize the packet with all the correct header information. And for that, what I recommend you do is just go grab one of those examples and then tweak the bits that you need to tweak yourself. And then you can send the packet. One of the other fun things you can do with raw sockets actually as well is you can also write a kind of your own packet sniffer. You can, with the raw socket, you can actually see all the packets that are happening on your network, which can be useful for debugging sometimes. Okay, and so then the way that the POC actually worked was it stuck these two values into the TCP options, and that's what triggers the bug, because this thing has to be multipath TCP, and then the second one, so I+1, is what gets written into there, and that makes bad things happen. So the thing that took me a little bit by surprise, when I first wrote the POC, it didn't seem to be working, and I couldn't quite figure out what was going on. And then my the Mac that I was using, seemed to have lost its internet access, and so that was puzzling me for a while. It actually took me about an hour to figure out what was going on, which is kind of embarrassing. It turned out that what I'd done was, rather than crashing the kernel, which is what I thought was going to happen, because this does appear to involve a stack buffer overflow, what actually ended up happening was it ended up getting stuck in an infinite loop. So this was more of a denial of service vulnerability, this 2017-13-904, where you could send a packet to the Mac and it would trigger an infinite loop, so that Mac is now running one of its cores at 100% and it can't connect to the internet anymore. Okay, so that bug, in fact, I reported to Apple in July of 2017, and it took a long time before I heard anything about it. So it wasn't until February 2018 that I got in touch with them to say, what's happened with this? Did you ever fix it? And they said, we fixed it in December. So I went back and looked at the code, and I honestly couldn't see what they changed in the code. I figured it out now. So if I go here and I select 10.13.3, which I think was the version that was out at that point, and I run the same query again, where is it? The only thing that they changed was they put a greater than in here. That didn't fix anything. I could still cause an infinite loop by basically just saying, well, what happened was I decided that it would be easier to use this one here. So I just made this value here be 0, and that means that the value of TCP oplen doesn't change, and so then this thing just gets stuck in an infinite loop. So I sent that back to them, and I said, it's not fixed. I can still cause an infinite loop. But the other thing, I guess I kind of had more confidence in the kernel developers at this point, where I thought that if I report a bug to them, then they're going to go over this code with a fine-tooth comb, and they're just going to fix everything. That's not what happened at all. I mean, they just did the minimum possible thing to basically fix the symptoms of the POC. So once I realized that they actually aren't as diligent as I thought they would be, I went back and started looking at this code more closely. And so the thing that I noticed then was this line here. So here, they're grabbing something again out of the TCP header, and then they're subtracting a number from it without checking that this isn't going to overflow. And then what happens is that that number gets copied into a ridge TCP oplen and gets plugged into this. Let me just make this a little smaller. They call mbuff copy data, and they pass this thing in. And at this point, where that parameter gets passed in, it gets cast to a size t. So if it is a negative number, then it wraps and becomes an enormous size t. So this was the point at which I started to learn kind of more interesting stuff about what to look for in XNU, because I looked at this function and started to figure out what it is. Okay. So first of all, this is the struct that defines the TCP header. That's the field that we were just looking at. What the purpose of this field is to tell you how big the options section is. So if you have no options, then the value of this should be 5, because what they do is it's the number of words of the header. So if it's 5, then that gets multiplied by 4 to give you 20, which is the basic size of a TCP header. And because it's a 4-bit number, you can go up to 15. So the maximum that it can be is 60 bytes. So you can have at most 40 bytes worth of options in the TCP header. But anything less than 5 is an illegal value, and you're supposed to check that. If you're working with raw TCP headers, then you're supposed to check that this number is less than 5. And they didn't do that, which is why they have this bug. So the next topic is what's an mbuff, because you saw in the code that they're doing stuff to do with mbuff. So what's an mbuff? Well, this is the type of an mbuff, which is I think not very helpful to look at. There's basically just a bunch of structs and unions. It's really impossible to tell what this thing does. In fact, I think they might as well just implemented it like this, because there's so little type safety there. So it's more instructive to look at the code that operates on mbuff. So this is the function that it was calling earlier, the mbuff copy data. And so this len value is the thing that we can make really huge in the packet mangler. And so what becomes clear now, as you look at this code, is that mbuff is a simply linked data structure, a linked list data structure. Because this first loop here, what that's doing is it's scanning through the linked list until it gets to the offset. Because what we're saying here is I want to copy this amount of data from this offset into this buffer. So first we need to scan forward through the linked list until we've got to the correct offset. And then in the second loop, that's when you can start copying. So one of the things that was interesting about this from the perspective of writing an exploit for it is that even though I've made this length length huge, this loop will stop as soon as it gets to the end of the linked list. So you can actually control the amount of data that's going to get written in your buffer overflow by the size of the amount of data that you send. It's not going to attempt to write 64 size t max amount of data. It's just going to go until it gets to the end of this linked list. And so that gives you a lot of control over what you can do there. Okay. In the code there, so the buff the place that we're writing into is a stack buffer. And so, in fact, this is a stack buffer overflow where you can send a network packet to the Mac, and it will write that data directly onto the stack. I did not. I mean, so Apple accredited me for finding an RCE for this. I didn't ever build an RCE. I'm not skilled enough to do that kind of kernel sort of hacking. So I just sent them the crash, and that's all I did. But yeah, they credit it as an RCE because this is the thing that you can overwrite, and it's on the stack. Okay. So what happened next? So I didn't notice this until, again, more than half a year later. The reason for this is that Apple are very slow to publish their source code. So that version of the source code that I was just showing you, 10.13.3, that was the only thing that was available until October of 2018. And so when it finally came out, when the updated source code was finally published, I went to see what they'd done, and it turned out that they'd not fixed one of the infinite loop bugs. So what they had fixed was they had fixed this one because that was the POC that I sent them. But you could get exactly the same effect by making this value 0. And so I was again able to get an infinite loop and another CV off them. Okay. So onto the second bug. So this time it was in the NFS client. Just to take you through the cartoon again. So that's Eve 999. And we've got a new villain here. This is Evil Pixel Blob, who is a living cube of energy. And what's happening here is that there's this kind of filing cabinet-like thing called KevFS. And Eve 999 unwisely wonders what the huge handle on the side of it is and decides to try moving the handle. Evil Pixel Blob makes a hasty exit. He was just finished hooking up the machine, and of course it explodes in Eve 999's face again. Okay, let me just show you what this looks like. So this time, let me just pause that. So I'm logged into the Mac. I'm on the guest account just to kind of demonstrate that this doesn't require any elevated privileges. Something that's interesting on macOS is that you can, as an ordinary user, you can mount NFS or other stuff as long as it's into a directory that you own. So if it's into your home directory, you're allowed to mount stuff. On my Linux machine, I'm not allowed to do this. I have to be root to mount NFS drives. But this was permissible. I think it still is in the guest account. And so that meant that I was able to mount the KevFS NFS drive that I'd created. And then this is what happens. So I mount the evil drive, and it reboots the machine. Okay. So although the packet mangle bug wasn't very exciting in itself, it did kind of help me along. So what I realized was that there's a bunch of these functions in XNU. There are XNU-specific things that are a lot like memcopies. I mean, so if you were looking for bugs in a regular application, then you'd probably be looking for memcopies where the size of the data that's being copied is too big and you get a buffer overflow. But that doesn't work on XNU because they're not using memcopy, they're using other stuff. So they've got this mbuff copy data, which is potentially pretty dangerous because it's working on mbuffs, and mbuffs are used for holding network data. And so that's potentially pretty dangerous. They also often use bcopy rather than memcopy for doing memcopies. And then these two functions, mbuff data and mtod, what they do is they grab the raw data pointer out of the mbuff. So the mbuff contains a bunch of bytes that have come in over the network, and you can use these two functions to actually just grab a pointer to that buffer and start reading it. So now that I knew about these functions, I could start writing data flow queries to look for places where they might be used in a dangerous way. So this query here, what I was looking for here was places where the sink is a bcopy. So bcopy is just a macro that expands to this built-in memmove thing. And the source is a place where we've grabbed a data pointer from an mbuff. So that's potentially tainted data that we've got there, and that looks like it might be flowing into the size argument of a bcopy. So if we run that, let me just grab the result immediately. So there's actually, you can see there's 23 results, and I got multiple CVEs for this because they made the same mistake in multiple places. But this is the query result that we get. That line there. The reason I'm showing you this one is this is the one that was the easiest. No, I'm showing you the wrong one. This one, 4151. This was the easiest one to trigger. The reason it's the easiest one to trigger is because it's in NFS3 mount. So this happens right at the first stages of mounting a drive. Is when this stuff happens. So it doesn't require a lot of implementation to do this. Some of the other bugs were in NFS v4. So macOS can do NFS v4 as a client. It cannot do NFS v4 as a server. But the client code for the NFS v4 had a lot of the same vulnerabilities as well. What I discovered is that kind of writing a fake NFS v4 server is a lot more complicated than writing an NFS v3 server. This cable is kind of... Okay, hope it stops flickering for you. Okay, so now looking at this line of code, it's not at all obvious that there's a bug here. This thing is a macro. Let me just show you this. Let's go here. So this file, nfsm subs.h, has got some epic macro programming in it. And so this is the definition of getfh. And let me actually just go back to my slides because I've got this on a slide. So there's a bunch of macros. This is the getfh. And what you see here is that it's reading a 32-bit value into fhlen, and then passing that 32-bit value into this getOpaque thing. And there's no bounds check here at all. So fhlen, what that's supposed to be is a file handle length. And on NFS v3, the length of the file handle should be at most 64 bytes. And on NFS v4, I think it's 128 bytes maximum. They didn't bother to check that. But of course, because it's been obscured in so many macros, it's kind of not obvious that that happened. But once I started to scrutinize this, I realized that, yeah, my query is right. This really is kind of dangerous. So on the next slide, I've got get opaque. And so you see that what get opaque does is it takes that len and it stuffs it directly into a bcopy. They also, I mean, yet another macro here. I don't have it on my slides, but this is the classic rounding up code, you know, where you kind of add 7 and then mod by, or do modulus by 8 in order to round the number up to the next multiple of 8. And so, of course, you can overflow that, make it wrap around to 0. So there was another bug right here in that macro. So what this meant was that you can write an NFS server, and when the Mac connects to the NFS server, the NFS server is supposed to send back a file handle, and you just send back a really big file handle, and that file handle will get just bcopied directly into the kernel memory. So essentially, as many bytes as you like. It's sort of unlimited what you could copy into the kernel. That goes into FH. I think there were multiple bugs. In some cases, FH was a stack pointer. And in some cases, FH was a heap pointer. So you kind of had a choice of whether or not you wanted to overflow the stack or if you wanted to overflow the heap. Okay. So how do you implement a fake NFS server? So this seemed like a really daunting task when I first was going to write a POC for this. It turns out that it's actually amazingly easy. So NFS uses something called RPC, and there's this tool called RPC Gen, which helps you to build RPC applications. The idea is that you don't, the NFS server doesn't need to open its own port. Instead, there's this kind of sort of generic entry point run by RPC that things connect to, and then the RPC server sort of delegates the work to the code that you've written. So it kind of provides the framework that does the network communication. All you need to do is write an application that implements the logic that's going to happen. And so, because the bug happens during the mounting operations, I didn't need to write very many of the RPC methods at all. I only needed to be able to handle the first couple of steps of the NFS protocol in order to trigger the bug. So it ended up just being 63 lines of RPC language and only 46 lines of C. So it was actually, in the end, remarkably easy to do. I did, at a later stage, also look into trying to write an NFS v4 server. That turned out to be quite a lot more complicated. And what I ended up doing was, instead, I'm still using RPC Gen, but what I instead did was made a kind of man in the middle. So I had like a genuine NFS server running, kind of sending back all the correct commands, most of which I would just pass on directly, and then I could just intercept the ones that I wanted to mess with and send that back to the Mac. So that code for the NFS v4 is not published because I didn't end up finding any, didn't end up actually triggering any exploits with it. But if you're interested in that, then do please get in touch with me, and I can show you that stuff. Okay. So this is kind of the main, the most important parts of that RPC file that I wrote, and so this is the this is the key one here. So this is the mount method. It gets a directory path, and then it's supposed to send back a file handle for that path. Normally, this file handle would be it would be defined as a 64-byte array, and all I did was I changed it so it was an unlimited size array, and so then I could send back more bytes and trigger the bug. So what happens when you run rpcgen on this is it generates some of the implementation for you, and it also generates some header files, and you just have to fill in the content of the functions. And so this is the main function that I had to implement. So they'd given me this signature here that I had to implement. And the key step here really is saying that the size is OX1000, and then plugging that in and returning it, and that triggered the bug. Okay, so moving on to the third and final bug. So we've got Eve999 here again. This villain here is called Mr. Litter. So what's happening here is he's sending another evil packet to Eve999, but this time Eve999's wise to it. And he says, ha, they're not doing this again, send it back. So he boxes it back up in an icomp box, and is going to send it back to Mr. Litter, but then it explodes in his face yet again. So let me show you the video. So it's kind of like the packet mangler, sending packets over Wi-Fi, but this time there's no kind of special configuration needed. So whereas with the packet mangler I had to go and do an admin command to switch on the packet mangler, this didn't require, it just works on vanilla macOS and iOS. All you needed to do was be on the same Wi-Fi network. If I remember, I'll explain why that is later, why you have to be on the same Wi-Fi network. Okay, so it's essentially the same thing that I was doing as before. I was just using a different combinations of sources and sinks for the data flow. So this time the source is this mtod thing, which is the function that grabs the data pointer out of the mbuff packet. And the sink is mcopydata. They've got a bit of code duplication in the kernel. So they've got like m_copydata, they've got mbuff_copydata. So that's why you need to look for both. Let me just run this one here. So this is the query. So you can see there, the source is mtod, and sink is copydata. Running that. Let me just pull it up immediately. So a few results, not all of them turned out to be interesting, but this one, so if I just show you the path here, so it thinks that the data comes from there. So this is all within a function called icomp error. And so you see it's got this argument here, which is an mbuff. And then it reads some stuff out of that mbuff. And then it does a bit of arithmetic on it, does a min operation on it, and then it sticks it into mcopydata. When I saw this, I was a little bit unsure as to whether or not this was a real vulnerability. It's kind of because it's all just in this this one function. It's a little bit unclear, and there's also a little bit of disbelief on my part. It's like this can't be real. I mean, surely somebody must have seen this before. One of the things that I forgot to mention earlier is mbuffs are used both for incoming and outgoing network messages. So it's a little bit unclear whether, I mean, this one could be one that we're sending. It might be completely trusted because it might be something that we're sending rather than something that we're receiving. So I had to do a bit of investigation to figure out, well, what is this icomp error thing? And is it possible for me to trigger it remotely? What I started out with was this query, where I basically just said, OK, I want the sink of the data flow, so the thing that it flows to be parameter 0 of the icomp error, because I want to know what this parameter is, where does it come from? And as the sources, I'm just going to say anything. I don't know. I'm just going to kind of look through them, see where might this come from. And so one of the things that you then see when you look at these results is that some of them actually do come from a function called IP input. Well, that sounds interesting, because that means it's coming from input, not output. So what I did then was I said, well, let's restrict the sources so that we only look at sources that are in the function called IP input, because they're likely to be the most interesting ones. So if we run that, and we get a smaller number of results. I'm sorry about the screen flickering like this. I guess it's because of the connection here. OK, so we got 8 results. So one of the things I noticed looking at these ones was that if you look at the paths, some of them, oh, that one looks like one of the real ones. Let me see if I've got another. Yeah, so a lot of them ended up going through this function called IP forward. Not totally sure what that is, but it sounded like a less sort of plausible attack vector to me, going through IP forward. So I decided to exclude those from the results. So that was the final tweak that I made to the query. I put in this barrier to say, I'm not interested if the data flow path goes through IP forward, then leave it out. I'm not interested in that. Let's wait a second to get the results. And so now we're down to 5 results. And so if we look at this one here, so it starts at mPullup. mPullup is a function that you see a lot in the kernel. What's happening is that mbuff is a linked list, and a lot of the time they're writing this really low-level kind of parsing code to sort of read the bytes that are in the buffer. And so in order to be able to do that, they want the bytes to be a continuous array of memory, which might not necessarily be the case because you've got this linked list of little chunks of data. And so they use this mPullup thing, and what that does is if the first element of the linked list is too small, so if the size of that first element is less than the size of a struct IP, then what they want to do is reallocate the memory, copy at least that number of bytes into the first element of the linked list so that they can then start reading it without accidentally going off the end. So that's what's going on here. And just to show you quickly, we are somewhere in the middle of this IP input function. These functions, by the way, that are doing the networking, it's unbelievable to me how kind of unstructured they seem. I mean, the worst offender is TCP input. It's over 3,000 lines long, and it's all this just super low-level bits and bytes type of stuff. So updating offsets and reading stuff out of the packet. I mean, it's so error-prone. What kind of hurts me is, I mean, before getting into security, my entire career was working as a compiler engineer, and so it hurts me when people don't trust the compiler to do optimizations for them. They feel that they have to take all of these things that should be little separate functions, they have to inline them themselves because they don't trust the compiler to do that for them. It really will work, I assure you. OK, so this one, it starts here. So this is an incoming IP packet. And then the next thing that happens is it goes into IP do options. And then inside IP do options, that's the parameter, there's then a possibility that if it hits this bad case, that it's going to call IP comp error. And so the way that you can make it hit that bad case, there's actually like plenty of opportunities. But basically, all you have to do is stick in a bad IP option. So if you just put an invalid IP option into the packet, then you're going to hit this bad case, and you go into the icomp error code down here, and then you end up in that parameter. So basically, to trigger this, all you have to do is send an IP packet that contains an invalid IP option, and you're going to hit this code. And then if you make that packet big enough, what it's going to do is so what I now understand is that icomp error, the idea is that if something goes wrong, then it sends out an icomp message saying something went wrong, this is the problem. And what it appears to be doing is copying the entirety of the incoming IP packet into the icomp packet in order to send it back out again. So if we just go back to my slide about the structure of the so if you make this thing as big as possible, so you can make the IP options be 40 bytes, and you can make the TCP options be 40 bytes, so then you've got 120 bytes here, and it turns out that that's big enough to make things go wrong in the packet mangler. Let me just go back to where it was. Not the packet mangler, the icomp error. Okay. Go back to presenting. So I guess the ironic thing about this is that the way that you trigger it is by turning a TCP packet, because that's how you get the biggest size of IP packet in order for it to stick into the icomp message and trigger the bug. So yeah, so there was one final little thing to this story, which is it did turn out that I was wrong about the reason that this crashed. So my query was looking for places where it was flowing into mcopy data. And so I wrote a blog post about this, and I got an email from Ian Beer, which is pretty cool to get an email from Ian Beer. And he actually knows how to debug the XNU kernel, and I don't. And so he'd stepped through this in the debugger, and it turns out that the place where it really crashes is on this line here. So it turns out that they're doing some kind of unwise stuff with casting to uint32 here, and it causes kind of a buffer overflow earlier in the code. So it was crashing for a different reason that I realized, but ultimately it didn't really matter too much. I mean, either way, you could crash the kernel. Okay. So it's my final slide. What's next? So I haven't been working on XNU recently. I've been looking at other open source projects. One of the main reasons for this is that, I'm still relatively inexperienced as a security researcher, and I'm keen to learn not just how to crash things, but also how to kind of like get code execution. And I don't think that doing that on the XNU kernel, where you can't just attach GDB to it, is the best place to start learning that. So I've been looking at some other projects where I can just fire up GDB and see what's happening. But does that mean that XNU's networking code is bug-free now? I certainly doubt it. You look at TCP input, it is absolutely massive. I find it hard to believe that they got every single line of that code right. So I would encourage anybody who's interested to go look at that code and see if you could find more bugs in it. And that's all from me. Thank you very much.